The next feature of the TCP protocol that I want to talk about is another feature that's really all about reliability, and that's the window size feature, which is really a field that's used in support of a broader feature set, which we'll refer to as flow control. If you think about packets going across the wire, there's a flow of those, and we think about things like bandwidth, where you only have so much bandwidth that you can only receive or send so many packets at a time. But we also have to have a concept of flow control on the individual host. When you think about it, a device, whether it's your laptop or a phone or so on, can only process information so fast. And there is also resource contention to think about, right? You have lots of processes running on your phone or on your desktop or on your laptop. And sometimes one process is going to take more CPU power or memory or something like that, more disk I/O than the other processes. And when that happens, the network has to be able to adjust for that, right? And that's where TCP flow control comes in, and that's specifically where this window size field comes in. So I want to talk through that. Now, you'll see that field. It's on the 1, 2, 3, 4th row there on the right. That's at TCP 14. That's a 2-byte field for window size. Now, what that window size basically specifies is the size of the TCP receive buffer. It's the size of the buffer that exists on the recipient device. So if I'm sending data to one device, whatever its TCP receive buffer is what's going to be the window size that's sent back from that in an acknowledgement packet. So again, I want to actually show this process, and I'll talk about it both in theory. We'll do that here in just a second, and then I'll actually show you where that field exists in some packets. Now, as I just mentioned, we have a couple concepts at play here. We have the TCP window size, which basically maps to what we call a sliding window or the TCP receive buffer on an individual host. So I think that's best illustrated by a diagram like the one you see on the screen here. In this case, we have a client device and we have a server. So the client has initiated communication, and it's actually sending data to the server. So not receiving from a server. In this case, we're actually sending it to a server. So this can be any protocol you want. Let's just say maybe it's an FTP connection and we're uploading data in this case. So we have a couple processes going on. These arrows here in the middle represent data being sent. We have the buffer space available, and that refers to the buffer space available on the server. And then we have the window size that's being communicated in the packets. Remember, that's a field within the TCP packet. In this case, you see that the window size is 5,000 bytes, and that's consistent the whole way through this communication. So we have a 5,000 byte window size, and it's not changing. We'll cover how that changes here in a minute. In this case, we have a client who sent 2,500 bytes to the server. Now, if our window size was 5,000, we subtract 2,500 from it, and we're left with 2,500 bytes available of buffer space. Now, the client in this case might send another 2,000 bytes. So at that point, we subtract those 2,000 from the 2,500 bytes available, and we're left with 500 bytes of available buffer space. So the question becomes, how do we refresh this buffer space? How do we know that there's more space available? Well, that actually comes in the acknowledgments to the data packets. And I mentioned there, in some cases, are acknowledgments for every data packet, but in other cases, there may only be acknowledgement for some via the usage of selective acknowledgement, which is a TCP option we'll talk about here in a moment. Now, in this case, we have 2 data packets sent followed by 1 acknowledgement. When that acknowledgement comes, what it does is it will have its window size value there. And if it doesn't change, if it's still 5,000 bytes, once the acknowledgement comes, the client system knows that the TCP receive window of 5,000 is now completely open because that data has been acknowledged. So now the buffer space goes back to 5,000 bytes as you see here. So that's the important thing to recognize. When the ACK comes back, whatever the window size is in that particular packet, and that TCP header is identifying what buffer space is available. So here in a minute, I'll show you that we can use that to transmit updates and change the window size, but in this case, it's staying the exact same. Once again, the client now sends 3,000 bytes, which reduces the buffer space from 5,000 to 2,000. We send another 1,000 bytes, which reduces it from 2,000 to 1,000. And then we get an acknowledgement wherein the window size is still 5,000 bytes, and we've got 5,000 bytes of buffer space available. The whole idea here is that the server, if it becomes overloaded, maybe it's got too much other network activity going on, maybe a process is running rampant, for whatever reason it can't process data fast enough, it can actually reduce the TCP receive window, reduce that window size down to slow the rate of data that's coming to it via TCP, and that's a pretty cool thing. It can actually even completely stop the rate of data coming to it. And we'll talk about that when we talk about troubleshooting latency later with TCP 0 windows and recoveries from those. But basically what you need to know is this is a flow control mechanism, and it can be used to slow down or halt the rate of traffic being sent from one device to another. Let's look at one more example of a TCP window update, but in this case, we'll have one where the TCP window is actually changing. Same scenario, we have a client sending data to a server. In this case, we start out with a window size of 5,000 bytes. You see that on the first line over here on the right. Now in this case, we send 2,000 bytes, and that reduces the buffer space available from 5,000 to 3,000. We send another 2,000 bytes, and that reduces it from 3,000 to 1,000. At this point, an acknowledgement comes back from the server, but notice that there is a window update to 1,000 bytes. And what that's basically saying is that the TCP receive window field is now set to 1,000. It was 5,000, it's now 1,000. So that tells us that the buffer space available is now 1,000 bytes for the next communication. So the client is going to adjust. It's only going to send, let's say it sends 800 bytes in the next packet. That's going to reduce the buffer size to 200 bytes. In the packet after that, it's going to send another 150 bytes, reducing the buffer space to 50 bytes. Now, this is just an example. This is not to say that this is the allocation or the distribution of how the host is going to send these things. But for this example, I'm just showing you it's slowing down the rate of communication because the window size is smaller. We finally have a final ACK here. There's no window size update here, so the window size remains 1,000 bytes, but buffer space is now available because the data has been acknowledged. If this were a temporary condition, then we might receive an ACK packet back at some point which says, okay, your your window size is now 5,000 again. You can raise your buffer to that. But that's how the window update process works, by examining that TCP window field within the TCP header. So that's enough theory. Let's actually get to the packets and look at some TCP window sizes. Now in this case, I'm looking at the same capture we've been looking at. It's just a simple HTTP transaction, which is writing over the top of TCP. In the first packet here, I'll expand this and we'll look at the window size value. In this case, it's 8,192 bytes, 8192. Now, one thing I mentioned earlier, it's important to know, is one of the reasons that the TCP handshake that we're going to talk about a little more later, one of the reasons it exists is to transmit window size values between both hosts. So you see here, from our source to destination, we're sending a window size value of 8192. And we go to the second packet, we're sending a Windows size value of 5720. So each endpoint in the conversation has its own window size value, because this is dependent upon the host and its ability to receive data and control the flow of information. So that's an important reason why we have the TCP handshake, not only things like initial sequence numbers, which we talked about, but also things like that. Now, I want to show you something else we haven't talked about to this point. One of the other reasons you would have this three-way handshake is to transmit TCP options to show what each endpoint supports in terms of expanded TCP functionality. Now, if I go to this first packet here and I go down to options, we'll talk about all these options later, but I just want to focus on one. If I expand that, notice we have an option that says window scale 2 multiplied by 4. Window scale is an option which allows an endpoint to specify a higher value than the maximum that is allowed in the window size field. Remember, window size is only a 2-byte field. You see that in the packet bytes window down there below. So what if you need a number that is much larger than that? What you can do is actually set this option, this window scale value, that says take whatever is in the window size field and multiply it. In this case, window scale is 2, so multiply by 4. And that allows you to get much bigger numbers for your TCP receive buffer than what you would have by default. Now, just because you can have those numbers doesn't mean you're going to use them. So, just multiplying 8192 by 4 in this case isn't going to breach the maximum value you can have for a 2-byte field. But a lot of systems will go ahead and include this if they support it, and just go ahead and use that multiplier for a case when that needs to occur. So in this case, you see this host is saying it supports a window scale of 2, so multiply by 4. and we go to the second host, we'll see it actually supports a Windows scale of 6 multiplied by 64. This is an operating system specific setting. It can actually be used to fingerprint operating systems a little bit. You can look at these fields and based upon what they are, make an educated guess about what an operating system is that you're communicating with, which is pretty neat when we talk about passive operating system identification. But nonetheless, Windows scale is an important option to consider when thinking about the actual value size. Now, since this is just the initial TCP handshake, you'll see that we're not doing that multiplication here. You see Windows size value is 5720. Calculated size is 5720. Since this is the handshake, we're not actually doing that math quite yet because both systems have to communicate that initial information first. But when we go to the next packet, you'll see that it actually is including that information with a proper calculation. Matter of fact, let's go ahead and go into to packet 4 here, and you'll see that now that this information has been communicated in the TCP handshake, in this case, we have a window size value of 4218, but we're also now have a calculated window size value of 16872. And Wireshark actually includes information here that's helpful to us. It says this is because there's a window scaling factor of 4. So we're multiplying 4218 and we come up with a window size of 16872. Now, one thing you can do here to, if you're ever doing some analysis where you need to examine window sizes and do it a little bit easier than just scrolling through, is to do one of my favorite actions, which is just to apply as a column. So in this case, I'm actually going to apply calculated window size. That's the one I want. I don't just want window size. I want the one that's compared against that TCP option for a multiplier. And that will give me this option up here where I now have calculated window size. Now, you'll notice the first couple packets where you're negotiating this information, we don't have those multipliers in place. But after that, we do. So we see that one host has a much bigger receive buffer than the other. But we also don't see any changes as well. So anything sent from 172.16.16.128 has a window size of 16,872. And anything sent from 74.125.95.104 has a window size of 6,976, in this case in bytes. So pretty cool, pretty straightforward. We talked about the concept and theory about it here. Later on when we talk about troubleshooting latency, we'll talk about what happens when a TCP window size goes down to 0, what happens when that fails, when it dies out, and what happens when it recovers eventually. So we'll talk about all those different aspects when we talk about latency and troubleshooting.